Hello, everyone. Welcome to the October session of CosmoVerse's Journal Club. Our today's first speaker is Rahul Shah. He is from Indian Statistical Institute, and he's going to talk about his work on revisiting the cosmic distance ladder with deep learning and approaches and exploring its application. Thank you, Rahul, and please start.
Thank you, Madhi. So, hello everyone. I'm Rahul from India. I'm currently a PhD student, as Madhi mentioned, at the Indian Statistical Institute in Kolkata. And my research interests primarily revolve around the prevalent and rising tensions and anomalies in contemporary cosmology, with my focus being on exploring the prospects of various statistical and machine learning techniques to study alternatives to the standard cosmological model, as well as model independent investigations of various cosmological issues. So before I delve into what I want to share today, I would like to extend my heartfelt gratitude to Enrico and Madhi and to CosmoVerse for this opportunity, and especially to Enrico for the motivation. So today I shall be talking about revisiting the cosmic distance ladder with deep learning approaches, and we'll also see some prospective applications of the same. So to begin with, a brief introduction to our whole existence, our universe. Of course, this is an overused graphic which shows the evolutionary history of our universe, and we are somewhere here on the right looking back in time. I want to take some time here and try to understand exactly what we are all trying to do in cosmology. Our aim is to develop a mathematical framework, a theory, which can describe the universe, this universe of ours, from the start to the finish. So any such theory, in most cases, cannot be derived purely empirically, and it would always have some free variables which need to be constrained from observations. So given a theory or a model, these free variables, which we call cosmological parameters, are what we want to constrain by looking at the universe. Now, here's the crucial part. Now, this point may seem trivial, but this point must never be forgotten. We have just one universe, which means the values of these parameters must be unique. So no matter how we measure these numbers, they should all be consistent with one another. So I'll come back to this point again. So before I proceed, let me quickly give an overview of our current understanding of the universe. Although this community does not require this introduction, our current understanding is based on the lambda cold dark matter model, which provides a very good fit to a wide range of observations, starting from late time supernovae to large scale structure observations, and finally the early time CMB and isotropy data. The cosmological constant, which is the simplest dark energy model, comprises nearly 69% of the total energy budget of the universe. About 26% of it is cold dark matter, and the most of the remaining stuff is the visible baryonic matter we see around us. Although this is a highly concordant model, there exist several open questions. For one, we are not yet sure as to the exact nature of dark energy, whether it is a cosmological constant or has a dynamic nature to it. Moreover, general relativity is the basis of this model, and whether it holds at cosmological scales is also under some debate, rather. Then there are hints of dark matter not being cold, and also the possibility of there being exotic interactions within the dark sector. Moreover, there is the issue of whether a universe is flat or closed and stuff like that. But why would we even think of such modifications in the first place if the standard model works so well? Well, the answer are the rising tensions and anomalies in the standard framework, which is what CosmoVerse is all about. So we yet do not know with absolute certainty as to what the origin of these tensions are, whether they are due to experimental systematics or whether they indicate yet undiscovered physics. So with that technical introduction of the standard model, let me come back to the fundamental goal of cosmology. Given a theory, we must measure its free parameters uniquely. Now, given the nature of our universe, most of these measurements are done by measuring distances to cosmic objects in one way or the other. However, doing this turns out to be a non-trivial matter, and people have come up with various techniques. I would like to discuss how distance measurements work in cosmology and how the so-called cosmic distance ladder is constructed. So on the left-hand side is a pictorial representation of the local distance ladder. Here, distances to astrophysical objects are measured starting from nearby galaxies and progressively moving farther away. For example, we start with geometrical measurements of Cepheid variables and then use their intrinsic properties to calibrate supernovae at slightly farther away galaxies. And then we move to even further away galaxies, which have very bright supernovae. Hence, this local distance ladder is cosmology independent, but it does have some astrophysical assumptions. Conversely, we can build up the so-called inverse distance ladder, where we start at the CMB. We infer the length of the sound horizon at drag epoch by assuming a cosmological model, and then extrapolate it to late times in order to calibrate supernovae and other datasets, such as BAO and so on. Hence, this inverse distance ladder is dependent on the assumed cosmological model. Or we could assume a parametric form of the Hubble parameter, or use the cosmographic series expansion, and hence reconstruct the distance ladder in a completely model-independent manner. But each of these methods have drawbacks. For example, the parametric reconstruction would have dependence on what sort of form we are taking. The cosmographic series expansion has some truncation errors, so we are not sure to what terms we should be taking those. So this is where the problem lies. Like, if we knew the actual cosmology, if we knew the correct way to construct the distance ladder, there should not be any discrepancy in any parameter. So yeah, so that's the problem. These different ways of measuring distances do not ultimately give unique values to cosmological parameters. And the most famous, or rather infamous, example is the Hubble tension. So for the uninitiated, the Hubble tension is a discrepancy in the measurement of the current rate of expansion of the universe when measurements are made from late time observations versus those from the early universe. But I'm not going to focus solely on the Hubble tension here. Rather, I want to focus on the fact that if we are indeed measuring distances uniquely and correctly, then there should not be any discrepancies in the inference of cosmological parameters, any of them in the first place. Of course, assuming that we are doing the experiments correctly. So I'm not considering systematics here. So herein lies the motivation of the current work. That is, it is important to revisit the cosmic distance ladder with a different technique, which is preferably model independent as well as non-parametric. So here we aim to do this using deep learning networks. So for now, we can gloss over the details, but the philosophy of deep learning is simply this. So let's say I have some data set, and the aim is to find out the underlying function describing this data without assuming any form for the function. So in the literature, there exists a wide range of deep learning models, but something that people don't keep in mind is each of these algorithms have caveats to them. Each of them have issues which have to do with underfitting and overfitting. So proper validation tests need to be done whenever applying any ML model to any cosmological application. Moreover, since our aim is to do precision cosmology, we want to have reliable predictions of error bars as well, error bars and uncertainties on the data, which can also then be extrapolated to redshifts beyond the available data range, or even data sparse regions, which is not an easy thing to do. So keeping these in mind, let me come to the main thing. So keeping these in mind, we propose a new deep learning framework that we call Ladder. The code is now publicly available on my GitHub page, which you can access from this link. Let me also put the link in the chat, or I'll probably do it at the end of the talk. And it is also featured on the CosmoVerse tools webpage. So any sequential data set with covariance information can in principle be used to train Ladder. But here we train it with the Pantheon supernovae compilation. We make use of the uncalibrated Pantheon dataset. We split the data into two parts, as usual, 80% for training and 20% for validation purposes. Given the Gaussian nature of the data, we make use of the KL divergence metric, which measures how two Gaussian, it measures how two different probability distributions vary, but we take the Gaussian form of this metric and use that as the loss function to train, test, and validate Ladder. So on the left here is the basic algorithm for Ladder, where we take into account both the systematic and the statistical uncertainties of the Pantheon compilation with the covariance information in order to reconstruct the cosmic distance ladder. But without going into the ML technical jargon, let me try to explain very, very intuitively how Ladder differs from conventional applications of such networks in this context. So usually, when you have a ML model, the way you train it is you feed data one by one into it and ask it to predict corresponding to some independent variable. But here what we do is we want to take into account the full covariance information, the full sequential nature of the data set. So we train as follows. So out of these 1,000 odd data points in Pantheon, we take about 30 data points. 30 is just an arbitrary number. Let's say I take 30 data points at random. And we construct a kind of multi-dimensional Gaussian distribution with this. How? We take into account the sub-matrix from the covariance matrix of these 30 points. And we also take into account the error, the errors on these measurements and construct kind of a multivariate Gaussian. Then we sample 30 points from this distribution and we feed it into the network. And then ask the ladder to predict the 31st point, some 31st point. Why do we get involved in this complication? The reason we do this is because Pantheon has this sequential nature to it. I mean, the farther you see, the distance will increase and stuff like that. And so we want to capture that sequential nature as much as possible rather than feeding data one at a time. The result of doing this is that the reconstruction is very, very stable. And it also has some decent extrapolation capabilities, which I shall discuss soon. So anyway, coming up with a fancy algorithm is all well and good, but it doesn't mean anything unless we can do proper validation tests. So, oh, by the way, I should mention that ladder is based on LSTM networks, which are like specialized for sequential data sets. Yeah, so coming back to the validation aspect. So we compared a few different network architectures and found out ladder to be the overall best performer based on how accurate it is, how accurate the predictions are, based on how smooth the reconstruction is, because we expect the universe to have evolved smoothly unless you are dealing with some non-trivial model. And we also ensure a monotonic reconstruction, since again, we expect distances to increase the farther we see, as I mentioned. And those are the metrics for the different cases. So without going into the details, what I want to stress upon is that similar validation metrics must always be used when applying any ML model to cosmology to ensure that there is no overfitting or underfitting. Right, so that is the network. If you have any questions on how exactly this works, I would love to discuss that. But let me, for now, move on to some possible applications of this. I hope I've been able to motivate why we are doing this. So yeah, so what do we have now? Now I'm going to make a very, very bold statement. This people are free to disagree with me on this. We now basically have a network which has learned the expansion history of the universe without assuming any cosmological model in a completely data-driven approach. We have not assumed any priors, no cosmological model, nothing, just based on the Pantheon dataset. So what applications could we have for this? So first, I want to talk about ladder being a consistency test with similar data sets. So when we speak of a similar data set, the first one that comes to mind is Pantheon Plus, which is an immediate successor of Pantheon, and it has a high data density at lower redshifts compared to the existing Pantheon compilation. So the plot on the left shows a comparison between the distribution of the two data sets in redshift space. Also, some concerns have been raised regarding Pantheon Plus, for example, the overestimation of errors or perhaps uncorrected systematics in the data set. With ladder, what we are trying to say is we are trying to investigate these concerns in an entirely model independent way. So having trained ladder on Pantheon, we asked ladder, well, what do you think Pantheon Plus would look like without showing it Pantheon? So basically it makes predictions at the Pantheon Plus redshifts. And in the second plot, you will see the blue shaded thing. The black line is the mean reconstruction and the blue is the 1 sigma spread of ladder reconstruction. And the black points are the Pantheon Plus data points. And we see that the reconstruction and the data points are consistent to 1 sigma. So it's quite a good reconstruction, so to say. But we wanted to quantify this more. How good is this reconstruction? So we kind of tried to constrain the parameters of lambda CDM and WCDM just as test cases for these three data sets: Pantheon, ladder predictions at Pantheon Plus redshifts, and Pantheon Plus. So in the third plot, and in the third and the fourth plot, you'll be able to see that we see that the ladder results trace the Pantheon results, which implies a good reconstruction in the case of both models. With Pantheon Plus for lambda CDM, we see a mean shift of matter density to a slightly higher value, and a slightly lower value in the case of WCDM, which is a result that has been found out through other methods, through other model independent methods in the literature. Here we see it in a completely model independent way. Also, the equation of state shows a preference for phantom for the ladder and Pantheon case, whereas a non-phantom equation of state for the Pantheon Plus. Anyway, I'm not focusing on the exact constraints. What is important is for all the three cases, despite these mild discrepancies, the constraints are consistent within the 1 sigma confidence level. So moving forward, I'll go to the second application that we have tried to kind of show in the paper, and I'll want to discuss here, is we focus on a comparative study between the transverse 2D bow and the anisotropic 3D bow datasets. The transverse bow dataset is model independent, whereas the anisotropic bow assumes a fiducial model for extracting the bow signal. In this exercise, we calibrate the bow datasets with ladder predictions and try to compare this ladder calibrated bow with the standard lambda CDM based bow calibration. Now, given the degeneracy between the supernova absolute magnitude and the co-moving sound horizon, we take the help of certain anchors as priors. So here we utilize the Shoes calibration on MB and the Planck prior on RD to break the degeneracy separately. So in the left panel, we show the plots and the solid contours are from ladder-based calibration, whereas the dashed contours are for the lambda CDM-based calibration. We find that the underlying cosmological model very closely resembles lambda CDM. There exists an internal inconsistency between the angular versus the isotropic bow data, which becomes very apparent in this figure. In these figures, we see that the anisotropic contours do not overlap, but the angular ones do. So this is an issue that has been reported in the literature before. I mean, angular bow being model independent and being consistent with both early and late time priors. But we are seeing this aspect here in using a completely model independent tool, and that is what we want to highlight. There is a issue with an isotropic bow data, perhaps, but it is apparent in a model independent way. Also, in the second plot on the right-hand side, if we club the 1 sigma uncertainties, the 1 sigma predictions from ladder, because I must remind you, ladder doesn't only predict the mean values, it also predicts the errors on its predictions. So if we incorporate those, we get wider error bars, of course, but it leads to a purely data-driven selection of the MB and RD parameter space, which can perhaps be useful in ruling out some alternative cosmological models. If there's some cosmological model which prefers MBRD values which are outside this model independent ladder space, probably they are not correct, probably. But of course, that caveat of Pantheon is always there. Right. With that, let me move to the final application which I want to show. And this is to do with the calibration of high redshift datasets. So here we consider gamma ray bursts, which a data set which is difficult to calibrate because it's such high redshift. I mean, it's not easy to extend your local distance ladder to those redshifts, but we can use ladder to calibrate it in a very model independent manner without assuming a cosmological model. So here we use the GRB to A219 sample, which has been split into two parts, low redshift and high redshift samples. For the low redshift samples, we cross-correlate them with the ladder reconstruction and make use of the Amati relation to obtain the GRB calibration parameters. Once this calibration is done, we now have a unique model-independent ladder-calibrated GRB dataset. And we can use this to do cosmology. We can use this to constrain any model that we want. So we just wanted to compare like the ladder calibration with the standard lambda CDM based calibration, and we obtain constraints for two different models. Again, lambda CDM and WCDM, just as a demonstration. And we find that the constraints obtained on the model parameters are consistent, irrespective of the calibration method. Again, the main takeaway here is that ladder enables us to calibrate such high redshift datasets in a purely data-driven approach. So with some of those applications, the way I guess I'm ahead of time, a lot ahead of time, but yeah, I would probably love to discuss on these with the audience. But let me summarize my key takeaways. The possibility of overfitting and underfitting issues in deep learning can, of course, lead to inaccurate and imprecise predictions in the context of cosmology. Hence, we propose ladder as a somewhat of an improvement that can learn sequential data utilizing the full covariance information within the data points. Reconstruction with ladder also exhibits stability even in data sparse regions that can give kind of give reliable predictions beyond the training data range. This can have one prospective application as a model independent mock data generator. For example, let's say to generate mock gravitational wave data sets in the context of forecast studies, in the context of like future GW missions. Finally, given ladder's potential, we hope this will open up new avenues for exploration in this direction in the future. So, as I mentioned already, ladder is now public. and it is available on my GitHub page. I strongly welcome everyone to use the code, play with it, and modify it as you see fit. I also encourage everyone to have a look at the corresponding paper, which contains more details of the work I presented and is now published in the Astrophysical Journal supplement series. Of course, I have to mention towards the end that this project was not a one-man job, and apart from support from two wonderful fellow cosmologists, we had invaluable expert input from ML scientists here at ISI Kolkata. So yeah, that kind of brings me to the end of my presentation, and I would love to hear your opinions and suggestions. And with this new algorithm, I'm excited to see what other applications we could have. So I really need everyone's inputs on this. And of course, if anyone has any questions, I'll try my best to answer those.